In this video, we discuss the instantaneous power. The instantaneous power, by the name suggests, that's the power at any given time. So let's look at this circuit here. We have V of t and I of t, and Z, that's any impedance. And this is AC circuit. They are sinusoid. Let's assume that V of t equals to Vm cosine omega t plus theta wave, and theta wave, that's the phase for the voltage. And I of t equals to Am cosine omega t plus theta I, and theta I is the phase of the current. So what's the instantaneous power? And you can see that the passive sign convention is followed. So P of t equals to V of t multiplied by I of t. We plug in V of t here and I of t here. Then we use this triple identity. Cosine A cosine B product equals to half cosine A minus B plus cosine A plus B. We obtain this equation here, the instantaneous power that equals to half Vm cosine theta wave minus theta I, and plus half Vm cosine, that's 2 omega t plus theta wave and theta I. That's exactly we applied this formula. The instantaneous power on this device contains a constant. This first term is not function of time, it's a constant. And second term is a function of time, it's cosine. The frequency becomes 2 omega. If we plot the instantaneous power with time, we can see power follows a cosine waveform on the top of a constant. Therefore, this is the constant. On top of this constant, the instantaneous power changing with the format of cosine. The magnitude of this cosine is half Vm Am. So this is the highest here is half Vm Am. We can see at some time the instantaneous power can go to negative values, and this is because the impedance contains inductors or capacitors. Those devices can store power or release power. We know for DC circuit and for pure resistance network, the power on the resistor always positive, cannot go negative. But in AC circuit, that's different scenario. Because the instantaneous power is changing with time, next let's introduce the average power. So the average power is the integral of the power from 0 to t and take the average over this time t. So this is average power. The reason we can do that because P of t is periodic. We can always take the average in one period and then divide it by the period. So we obtain the average power. This is a formula to obtain the average power. Either we memorize it or we put it in the formula sheet. If we take the average of the power, that's instantaneous power. This is a cosine signal. If we take cosine signal in one period, the integral will become 0. You can see this is the cosine waveform that's come from this term. The integral will be the area below this curve. If we consider this dotted line here, positive, positive, negative, positive, negative. So integral on this term goes to 0. The average power is determined by this term. Therefore, the average power equals to half Vm cosine theta wave minus theta I. That's the phase difference between the voltage and the current. And this is also equal to half real part of a phasor V and conjugate of I. Let's see how this is true. we know that for in phasor domain, V equals to Vm theta V, that's phasor, that equals to Vm e to power j theta V. And I equals to Im theta I, that equals to Im e to power j theta I. If we look at it, V multiplied by I conjugate, that equals to Vm multiplied by Im, and e to power j theta V minus theta I. And if we take Euler's formula, so Euler's formula, this is the Euler's formula applied to here. That's equals cosine theta V minus theta I plus j sine theta V minus theta I. If we take the real part, that's equals to Vm Im cosine, this portion here. And then if we take half, there's a half here, there's a scale half of there. Therefore, this portion is equals to half real part of V multiplied by conjugate I in the phasor domain. So all of these formulas we want to know. We cannot memorize everything. Later on, we're going to have more formulas. We suggest that we create a formula sheet. Next, let's introduce two concepts. One is resistive circuit. Another one is reactive circuit. What does that mean? If we look at this, V equals to Vm, that's phasor domain, theta V, and this is Im, theta I, that's for the current, and this is the impedance. If theta V equals theta I, then impedance must be equals to R, which means that this impedance does not have imaginary part. That will make the current and the voltage in phase. So in this case, the circuit becomes pure resistive. It's just a resistor here. Z equals to R, X equals to 0. In this case, the average power equals to half Vm Im because cosine 0 equals to 1. Vm in this case equals to Im multiplied by R. So this equals to half Im squared multiplied by R. And this notation, that's the magnitude of I is the phasor. That's complex numbers. This notation here, that's the magnitude of the complex number I. We can see this quantity always greater than 0. What about if theta V minus theta I equals to plus or negative 90 degrees? In this case, P equals to half Vm cosine plus or negative 90 degrees, doesn't matter, that equals 0. In this case, the impedance here does not have any real part. They only have imaginary part. So the circuits become pure reactive. The word reactive is that the device does not absorb any power. In other words, this device can be inductor or capacitor and without any resistors.